Yes, we can see.
Okay. All right. Thanks for having me. My name is Henok, and I'm joining you from Colorado this evening. I know it's morning time over there. And I'm here to present sort of my last piece on what I've been working on for the last about 6-7 years. My expertise is convolutional networks, and I've been working to try and basically produce robust models using different techniques. And this piece is particularly addressing adversary attacks using some of the algorithms that we've come up with in the past 7 years. I'm going to go ahead and do a brief introduction and give you the background for both the attack and defense research domain, and then sort of switch up to discussing the proposed method before I start talking about highlighting the key findings and opening it up to questions. So, as you know, as you know, AI models, I want to say that we're in sort of AI emergency situation in the current age. And we are deploying a lot of AI models into safety critical production environments, including medical and security settings. So as a result, you do want to be concerned about how these models can be attacked and what the best way of preventing those attacks is. Okay. So convolutional neural networks, those of you that are not familiar with these models, they're primarily designed to tackle image or video types of data sets. And they are the ones that have been superb at image classification and object detection tasks. In fact, CNNs were the first ones that sort of outperformed traditional methodologies as far as, and that propelled deep learning into the forefront of machine learning. And if you remember, 2012 was the first CNN model that did a breakthrough on the ImageNet dataset. They are very accurate in image recognition tasks, and I've deployed a few models in production, and I've also developed. I've worked with most of the state-of-the-art models, and I will assure you that their performance is actually quite high. And they're very efficient at extracting features from two-dimensional data sets, be it images or video streams. We're using them in medical imaging, and we're using them for security purposes. These are sort of the two example use cases I want to bring up as sort of the key domains that require security of these models. CNNs for detecting anomalies in X-rays is a good example. And as far as security is concerned, facial recognition systems, just like fingerprints, can be used to secure systems, and you want to be sure that the facial recognition system is not tampered with as far as adversary and security is concerned. Okay. So these models are very successful. We know they can do a lot in both research and practical domains. However, they're also easy to attack, and they're also easy to fool. What I'm showing you here is called sort of the foundation of adversary attack. And this is one particular example that I'm sharing here, but on the left side is the original stop sign, and the model that was trained on these images can accurately classify it as a stop sign. But after it was tampered with, after the input data was tampered with, say a patch, that causes the model to completely misclassify that image as a speed limit 80 sign. So, and I don't have to say a whole lot to clarify the security implications of this type of attack, or the implications of these types of attacks. Okay. So what is adversary attack, or what is this research domain? You are interested in modifying and as far as CNNs are concerned, you're interested in modifying the input image such that the fully trained model, the fully trained and accurate model is fooled, essentially. And these can be as minute, these attacks can be as minute as perturbing or changing a single pixel within an entire image. And these attacks to the human eye they might not be visible to the human eye. Some of the attacks are. Some of them are imperceptible by the human eye, especially if they're doing pixel modifications that the human eye is not able to capture. And what I'm showing you here, the example on the right side, or the image on the right side is called a 1 pixel attack. And you modify that 1 pixel, or you attack 1 pixel within the entire region to cause the CNN to completely misclassify that image. Okay. So in a sort of formal way, the objective of an attack is to modify an image X such that so to add a perturbation to the image X such that the output of the model is different, okay, with and without the perturbation. So we have F as the trained model here, and you have X plus R as the perturbed image or modified image, and R being the perturbation in this case. So it can be just modifying a single pixel in that image or adding a patch to that image. Regardless of what R is, X plus R becomes sort of the perturbed image. And when you run that image through the model, through the trained model, you end up getting a result that's different than the original. Okay. Sort of what I'm talking about. You have the original image X is classified as a cat by the model F, and you end up adding a perturbation, in this case, a 1 pixel perturbation, to cause that model to misclassify that same image as a dog. There are various types of attacks. I kind of want to hone in. I'll briefly mention the other ones too, but I want to hone in on the targeted and untargeted attacks. If it is a targeted attack, you're interested in producing a specific output. So in that setting, not only do you provide the original image, but also you say, hey, this is the output I want it to be after the attack, i.e., I want the cat to be classified as a parrot. So you provide not only the desired output, but also the image, okay? And you supply that, you add perturbation to that image, and then you end up producing a result that is a parrot, okay? So you have a targeted class in this case. If it is a targeted attack, you supply a target class for the attack, okay? And you can sort of extrapolate here. If it is untargeted, then you basically want to modify the input image such that the output is different than the original. Okay. In this context, you don't necessarily have to have a target output. Okay. As long as the output is different from the original one or from the correct one, that is called untargeted attack. Or in some cases, this can also be labeled a universal attack. Okay. There is a taxonomy of attacks. I kind of want to highlight a few of them: black box, white box. The way you classify these attacks is as black box versus white boxes, depending on the knowledge of the amount of knowledge you have about the model itself. So if the attack is called black box attack, then the attacker has no knowledge of the model itself. If it is a white box attack, however, the attacker knows enough about the model that is being attacked. It knows the architecture, the number of layers, the weights, its sensitivity to certain classes, et cetera, et cetera. Okay. You can also have physical attacks. There has been some physical attacks that you can, just like that sticker on the stop sign I showed you. You can produce these stickers to actually put them on physical systems as a way to confuse the digital model. Okay. So there's a few of them, but I kind of wanted to mention these taxonomies. That way you have some awareness. Okay. There are also so many different types of attack techniques. In this publication, I'm addressing 2 types of attacks, and you will probably see why that is the case. One pixel attack is basically modifying one pixel to effectively produce a different output or to effectively fool the model. There is also a attack type called adversary patch attack. In this case, a patch is produced by sort of training a model. So you use the generative adversarial models to produce these patches, but that GAN model it learns how to produce that patch from the model that is being attacked. So in a sense, this is a white box attack type. There are fast gradient sign methods that sort of try to manipulate the underlying model performance or the underlying model prediction by modifying the gradients, okay, during the gradients that it calculates during the forward pass at inference time. You can also have projected gradient descent. And this is an approach that aims to find a maximally effective perturbation by sort of doing a gradient descent or gradient ascent approaches. So almost like training a separate model that decides, hey, these are the types of perturbations you should apply. And one pixel, in a sense, uses this type of iterative approach. It basically learns how to modify that one pixel, which pixel to modify by doing this iterative gradient descent in order to find the maximum perturbation. Deep fool, in this case, this is the sort of the opposite of PGD. It attempts to find the smallest perturbation that misleads the model. Okay, and these are only a few. I do suggest you read a few survey papers that are out there if you want to have a sort of a deeper and breadthful grasp of all these different attack types. Okay, so why do we care? I think I sort of tried to allude to this in my introduction. You're concerned with safety risks. I mean, hey, the self-driving cars are becoming a reality nowadays. Misdiagnosis in medical settings. Okay, and professionally, I've worked in medical domain in the past, and one of the systems I worked on was an X-ray, a cancerous lesion detection system from X-rays, and imagine sort of misclassifying a cancer patient or misdiagnosing a cancer patient. That can mean life loss, but also there's monetary value associated, monetary cost associated with that misdiagnosis. And then security, as in, banks and other places. Okay. As far as the sort of companies or the stakeholders are concerned, there is a loss of public trust, but there is also legal and ethical implications, and not to mention there is monetary costs associated with all of this. So those are the implications. And there is, I'm not particularly focused on adversary research per se. I'm more in sort of in the sort of building these models, understanding their internal configurations. But there is a sort of a full and complete research domain that is focused on adversary research. If you want to look into it, but in any case, so a few highlights from the news that sort of briefly describe the implications of having these models secure. Okay, somebody sleeping on a self-driving car is an example. Okay. So I want to kind of this sort of came about by accident, to be honest. These algorithms that I'm going to be describing were designed for different purposes, but we decided to explore how effective they are at defending these particular types of attacks. Localized universal attacks, meaning the attacks are usually confined to a small region. If you can see with these 1-pixel attacks, and if you can see the patch attack that is on the stop sign, that is also localized to a contiguous region within the entire image. Okay. And we also expect that those attacked pixels to be much less than the total number of pixels. Okay. So that is sort of a brief background on attacks. Now, so what are people doing as far as defending these attacks are concerned? Basically, you want to develop methodologies to protect against these attacks. In some cases, you want to understand what these attacks are. In another case, you want to basically produce robust models, certified models that sort of that do not drift or that do underperform under these attack conditions. Okay. So I will highlight a couple of those research items from both of those. You want to maintain model accuracy and generalizability. Maintain robustness to evasion. Okay, you should be able to detect that the model is being attacked, and if somebody is trying to evade somehow by determining that this is a sort of attack agnostic or attack aware model, then you should be able to circumnavigate that. You should be able to sort of keep an eye on the evasion techniques they're employing. Okay, so a couple of references for those of you interested in reading about defense. Ultimately, the defense objective is to maximize a loss over all the possible adversary examples. Minimize and maximize the maximum loss. Okay, so given some perturbation that is being applied to the image X, you want to minimize the total loss by the model under that perturbation, given that perturbation of the image. Okay, so you have a data set, say take a CIFAR-10 data set, and you have a model that is attacking CIFAR-10 data set. Well, take the original data of CIFAR-10, train that model, that defended model on CIFAR-10 clean data, train that same model on CIFAR-10 attack data, and then make sure that you're minimizing the loss under the attack condition. And that will lead you to sort of a defended model. Okay, this is what you want to do with when you're looking into defending a model against adversary attack. Okay, so sort of restating my research focus as far as this presentation is concerned. We want to defend against localized attacks, but we want to also make sure that the perturbations are localized and that the perturbed pixels are much less than the number of pixels in the entire image. Okay? They're small perturbations, not large perturbations, okay? So again, I'm focused on one pixel and adversary attacks. There are a few others that can be classified as universal and localized attacks. And some variants of these attacks as well can be classified as that. Okay. There are three different types of defense approaches, I want to say: proactive, detection, and reactive. Proactive defense is you can rely on adversary training. Actually, I'm starting on this reactive defense. With reactive defense, you can utilize adversary training. That is to say, take CIFAR-10 dataset and add the dataset that was attacked to that same CIFAR-10 dataset. So CIFAR-10 plus CIFAR-10 attack dataset, and then train your model. So the model would be aware of not only CIFAR-10 features of those 10 different classes, but it would also be aware of the attacks, right? In this case, it would be aware of those specific attacks that are placed on the dataset. So this approach is called adversary training. You can also do defense distillation. The approach with defense distillation is to basically take a look at the gradients, i.e., take a look at the outputs of the models, and sort of the probabilities are softened in this attitude, and then you take the initial during your initial pass, you train the model so that it produces softened probabilities, and people do not necessarily have to. The attackers do not have the sort of purview into the model's decision process, because all of the probabilities are softened, that it is difficult to determine what the useful gradients are as far as the model is concerned. And then in the second pass, you take the original softened model, or the model that was trained to output softened probabilities, and teach a student model. And then at that point, the student model can be deployed, and it will have less sensitivity to small changes in the input, partly because because of the setup. Okay. So this is called defense distillation approach. The detection-based defense is if I have a set of pixels attacked within the image. The purpose is to automatically identify those attacked pixels and remedy the attack. Okay. You can effectively reject these inputs in a operational setting if it is a critical operational setting, like say medical conditions or medical diagnosis. Or you can, there are some researchers proposing that you actually do in-painting or modify the input so that the attacked pixels are removed. But there are risks associated with that. So that adversary detection networks. So the out-of-bound distribution detection is you can look at the entire distribution of the pixels and then identify, hey, are any of these pixels attacked pixels? In the adversary detection setting, you're actually looking for the adversary itself. So if I have a patch on a given image, you try to identify that patch. Sort of like, just maybe you can implement a object detection approach on that image, identify the attacked pixels, and then perhaps remove them, or again, reject the input altogether. Proactive defense, this is almost you want your model to be attack agnostic or attack pixels agnostic, and that you don't want it to know anything about attacks, but you want it to be robust against attacks. So that's sort of the proactive defense. So you don't necessarily have to employ adversary training, or you implement detection mechanisms into the models, but you somehow come up with a technique to produce models that are accurate on clean data, but also are effective at defending against adversary attacks at the same time. So this is called proactive defense. So input reconstruction is one option. Feature squeezing is another one that has been proposed out there. Okay. And our method can be classified as a proactive defense method that is focused on adversary attacks or on localized adversary attacks. It is also based on input reconstruction. Okay, I'll highlight what the methodology we're using looks like. It uses 3D convolution or just 3D input volume. And I'll highlight again the algorithm that allows us to do something like that. Also leverages curriculum learning in this context. Although I have to say from the get-go that the curriculum learning part is not necessarily designed to make the model itself robust against these attacks. I would say the 3D convolution and the algorithm that does a reconstruction perhaps takes more of the credit for defending against these attacks. Okay, so this is actually called the volumization algorithm. Okay, so I just mentioned a few key tenets of the approach: curriculum learning optimization, volumization algorithm, and 3D convolution. So let me quickly step through all of those, give you sort of an overview. If you're not aware of curriculum learning, it is basically what humans do in our educational systems, but doing that with these models. Okay, when we train models, we're not just training models using shuffled data, but we are applying a certain curriculum. Okay, that's what curriculum learning means in the context of deep learning. And this was originally proposed by Benjo and his team. And it's basically train models progressively start off with simple data points and then gradually increase the complexity of the data points as you train. And we know curriculum learning works from human experience. And if you want to sort of think about it, just go back to your college days. You might be in college still, but go back to your college days, think about, or maybe high school, think about your math course progression. You have to start with some basics. Having grasped the basics helps you understand algebra better, and then having understood the concepts of algebra becomes critical in understanding and grasping calculus, and further grasping differential equations, numerical analysis, etc., etc. Okay, so you gradually increase the complexity or introduce more complex subjects as you progress. Okay, so this is what you want to do when you're training models as well. So I'm gonna my whole research is actually centered around curriculum learning. So I'm going to go ahead and present what is called deep curriculum learning optimization. This is a framework that exists. And the approach I use is basically, if you remember, if you're aware, if you train model, you're aware of how you train models. You typically set a batch parameter and sample that batch, and then you pass that. You also have a set of hyperparameters. You pass that to a model, and the model learns, and then you backpropagate the errors depending on the hyperparameters that you specified. How often you modify the weights depends on the the learning rate and the other parameters you specify, hyperparameters you specify. In curriculum learning setting, what you do is you don't just random shuffle and present that data to the training system, to the model. Instead, you're trying to determine, hey, how should I feed these images to the model such that it learns faster, and it generalizes better at the end of the day. Okay, so the approach we've taken in implementing this framework was we basically use complexity metrics that capture the inherent characteristics of these models, and assess, inherent characteristics of these data sets or these images. So for every image in the batch, you assess and rank it. And then you sort the batch in order according to the value of the rank. Okay. And then you construct a syllabus. A syllabus in this case is basically an ordering of the batch or the samplers within the batch according to the rank that you calculated for each image. You take that syllabus, you take the original batch, you train the model. So the key difference here is you're not just random shuffling and supplying that batch to the model. Instead, you're deciding a syllabus on how to supply those images in the batch, in what order to supply those images in the batch to the model. Okay. And then eventually, this framework allows us to further determine if that syllabus is fit or not fit on that particular data set. So there is sort of, it makes it adaptive and fit for real-time deep learning trainings. Okay. You're welcome to stop me if you have any questions. So that's what curriculum learning is in a nutshell. There are different ways you can approach the assessment of the samples themselves. There are some researchers out there that train models twice. The first time to determine how the model is reacting to each data point in the data set. And then in the second pass, they take what they observed in the first pass and then supply the images in a certain order in the second pass. Obviously, that is computer intensive, but we're trying to sort of, as an option, we're trying to do this. We present a sort of inherent way to characterize these samples. So DeepCNO utilizes natural image characteristics. It doesn't presume difficulty, doesn't consult the models to determine what is optimal, what is complex, what is not complex sample. It is dynamic, and it can evaluate the syllabus that it proposes. And it is also doesn't force you to modify the objective function. You can just take the network loss, the native loss function that is implemented in the network, and use that as a way to determine how well the model is reacting to the syllabus you propose. And we've integrated this into the deep learning, and it is a plug and play approach. Okay, so that is the curriculum learning, sort of the general approach that we used in this research, or the training methodology we use in this research. The other key component is called a volumization algorithm. That's just a name that we came up with, partly because it takes a two-dimensional image and produces a three-dimensional volume. Okay, and then we take that. Okay, let me actually go through the steps. So you give me an image with height and width and a colored image, and this algorithm, what it does is it proposes a patching approach. In the first step, it basically splits the image into different patches, and you can supply a hyperparameter like PW, PH can be supplied as hyperparameters. And then in the third pass, or in the second pass in this context, it evaluates each patch in the image, okay? Just the same way we do it, and we evaluate each image in a batch during curriculum learning, and then it basically ranks them and orders them, and then it constructs a new input according to that order. Okay, so you're going from a two-dimensional image to a three-dimensional volume at the end of the day with this algorithm. Okay, keep in mind as I speak about this, the vision transformer model adapts transformer models approach, but they also do patching of images, and then they supply those images as a sequence of data points. The same way transformer models take a sequence of characters, sentences, or words. Okay, it takes, so the vision transformer model, which is I think the state of the art in image classification now, takes a similar approach. So the only condition we enforce here is to sort of for validation purposes, for integrity purposes, that the model, the transformation approach doesn't modify any of the pixels in the original image. So it maintains all the pixels. Okay. It allows you to create 3D volumes to do 3D convolution, and then my argument is that is actually that provides a nuanced view into each sample. Okay, and then as far as the models are concerned, it provides enhanced sensitivity to local features, and then obviously it increases the number of data points you can play around with when you split up the image into multiple patches. Okay. And then as far as in relation to adversary attacks, my intuition is that the attack can be confined to one of the patches, and the model should be able to not be affected as much if it were trained, as much as it would have been affected if it were trained without the patching process or without the volumized input. Okay. But then again, that's why we're doing this. We're presenting some of the results that give support to that claim in this case. And then the reason I came up with this algorithm is actually because I was working with a lot of MRI data that those of you who work with MRI data, you know that there are slices and they're volumetric data, volumetric images. Okay, so I mentioned that we analyze each image or each patch within an image to understand its sort of inherent characteristics. And some of the complexity metrics we use come from information theory, some of them come from statistics. If you can see here, we use, for instance, peak signal to noise ratio. This is a common metric used in codecs for sort of reconstructing video streams. We also use things like entropy, and entropy captures the sort of randomness of an information source as you send it through a reliable channel. Okay. So these are the, and I'll show you some samples on how these metrics show up for different images. Okay, so what we have deep learning, and then we have to modify each sample to be 3D volume. And if that's the case, then we have to also modify the models to actually do proper feature extraction. Okay. So in that case, we have to modify the model architectures to do 3D convolution, and then every layer in the model has to be modified to be compatible with 3D input. And then that sort of introduces a number of parameter increase in a lot of models. I'll show a table that shows that, but that is the complexity trade-off that I want to argue you're able to tolerate. Parameter increase usually translates into it will take more time to train these models. Okay, so combine all of them together. This is sort of the proposed end-to-end training approach. Okay, given some hyperparameters, we take a metric, complexity metric to be used in curriculum, and then a volumization. You take the patch size and then how you want to order things. So those can be specified as hyperparameters. You sample a batch from the data set. You generate a syllabus using the Deep CLO framework. And then you take that sort of reordered batch of images using that syllabus, and then start applying the volumization on those images. And I'm showing this sort of in a real-time sense in during training. Split each image into individual patches, assess each patch or slice, and then construct your volume. So that's the volumization component. So apply that volume to the model. And then on each patch, keep in mind here, we're training the model on each individual patch in this case. But we know that each patch in the image belongs to a single image or a single label. So we aggregate the loss into what is called a patch aggregate loss. And then we do the update after aggregating the loss on individual patch. So we don't necessarily update the model on the individual patch loss, but we aggregate the losses first, and then we do the update of the model, okay? And then you proceed to the next epoch, okay? So that's sort of the overall system end-to-end training. And we did some experiments on this. So just to talk about some details on the experimentation, we implemented this. This framework has been around for some time now, but it's in TensorFlow Keras-based. And then the adversary component is implemented using a library called Fullbox. And then we use CIFAR-10 and 100, and then the ImageNet dataset for experimentation. We present the classification accuracy. How does the model perform and when there aren't any attacks? That's ACC clean. How does the model perform when all the test set is attacked? Okay, ACC attack. The model robustness is defined as the difference between the two. Okay? The performance loss as if the ACC clean minus ACC attack, that captures how robust the model is. And the smaller it is, the better, okay? Defense success rate is the percentage of successfully defended adversarial attacks. This sort of allows you to capture the real-time scenario. Some of the images can be attacked, and we take that approach. 50% of them are attacked, and then you calculate the defense success rate as the percentage of successfully defended attacks. And then we also could make ablation study to at least understand the impact of curriculum learning versus the volumization algorithm, and then also to understand, although this may not be an ablation study, the volume depth, to understand the impact of the volume depth on defense. I'll present some of those results. We use these models for this research, and then, like I mentioned, the technique that we used here forces the modification of the model architecture, and these are the increase in parameters that you get if you go, for instance, for VGG16, you go from 143 to 183. That's a million. That's almost a 40 million increase. Okay, but I argue that is tolerable given the increase and robustness against adversary attacks. We for comparison analysis, like I said, evaluation study on one pixel adversary attack, untargeted, and then only image classification models. The adversary patch attack, you can apply different types of patches. And we take these 4 patches or 5 patches. We consider only these 5 patches for this experiment, and that is, I should have added the reference here, but it is one of the seminal papers that introduced adversary patch attacks. So we use the AADS synthesizing approach to synthesize these images. Okay. So I'm gonna start from sort of the basics here. When you train a model and using this particular proposed approach, what do you see? And as far as the setting, the patch size is 16 by 16, i.e. each image, for instance, in CIFAR-10, you have 32 by 32. But for each image, we produce a sort of four slices. Okay, so that's what it means, 16 by 16. And we notice there is a high defense success rate during training. There is the model learned just fine, but also when you attack the models during validation study, you don't see them produce low accuracy during training. Okay. So that's what you see in here. The accuracy, the undefended model, when you introduce these attacks, drops down for obvious reasons, but the ones that are defended without approaches do maintain a level of high accuracy, or at least there is a delta between the undefended and the defended models. Just making observations during training. Defense effectiveness when you apply on a test set. That is, you take CIFAR-10, 10,000 held out data sets, attack all of those, and then do this analysis to determine how well the model is performing under our proposed approach. Okay. Again, we also noticed strong performance of the defended models under adversary attack. Please notice the attack columns here. And then if you look at the undefended model, the performance of it significantly drops when you attack the test set. Again, that is really the purpose of these attacks, so you expect that to be the case. And our hope was to try and produce, or at least maintain, a level of accuracy that is better when you apply the proposed method. Okay, and we see that with almost all of them. When we apply our method, the performance is retained or is better than the undefended under attack conditions, although I wouldn't say the same under no attack conditions. So the undefended model does as well, in fact, better in some cases, but not in the attack setting. Okay. Defense effectiveness, this is sort of trying to understand, well, how well are you actually defending? So we various variables here. For instance, the patch size, the coverage of the patch attack varies here from 5% to 25%, okay? And then in the upper plot, we increase the number of attacked pixels from 1 to 15, okay? And we notice that as we increase the attack magnitude, that even the defended models start to perform less. So the defense of the defended models starts to wane down as you increase the attack magnitude. Okay, and the intuition for that is the attacked pixels are now growing, and they are surpassing the number of patch or the individual patch size in the volume, and it's probably incorrectly misclassifying more than one patch in the volume, producing overall incorrect result. I guess the key findings are attack magnitude reduces the model performance. And then by implication, the defense success rate also decreases. So this is to say, hey, the model's actually, the defense methodology is effective only at defending localized and small attacks, which is the valuable result. Okay. Comparative study. So this is to try and understand how this particular proposed methodology fares against other results in the literature. Okay, so we compare against a few proactive defense techniques and then detection-based techniques. Okay, and these are the results. It is actually difficult to do a fair comparison, partly because our approach is it takes an existing model and tries to certify that model against a specific attack. Okay. But if you take, for instance, the PSD approach or Liu et al. Approach, or in the adversary patch methods that we compare against, some of them, they use their own models. Some of them also don't necessarily use the same models that we're using in this case. Okay. However, they use the similar data set. So for instance, this is defending against CIFAR-10 data set. So that's how I want to present this comparative result. This is, hey, we produce these models, we can achieve almost 100% accurate model. We can produce 100% accurate model on CIFAR-10 data set. Well, how about successfully defended model on CIFAR-10 data set? So that's how I want to read it, instead of kind of highlighting the models that are in use in this case. In any case, we perform, at least in the case of PSD and Liu et al., on the VGG model, that use VGG model, we outperform it. The undefended model obviously does really bad in attack settings, and the other ones don't necessarily use efficient nets for their studies. Okay. So by far, this is the state of the art on at least one pixel attack and CIFAR-10 dataset in terms of defended models, fully certified models. Okay. On the adversary patch attack, we we were faced with similar limitations. A lot of them report results in CIFAR-100, CIFAR-10. A lot of people use CIFAR-10 and CIFAR-100 as sort of the initial benchmark data sets, but most also produce results on the ImageNet. And we tried to gather as many of them as possible and present those results here to the extent we could. Okay. And here I'm presenting two of ours, mutual information defended ResNet, and then PSNR defended inception model. Okay. And then if you see PSNR outperforms everybody else on CIFAR-10 and 100, at least the ones that report results. And then on the CIFAR-10 dataset, the mutual information based ResNet model outperforms everybody else. And keep in mind, however, I want to present this result as a best performance on the data set. And I don't want to mention any models in this case. And some of these guys, VaxNet, DW, is Inception and VGG. How do they perform on CIFAR on a ImageNet? That's how I'm kind of reading it. This is the VIT, Vision Transformer model, trained just without any modifications to defend against adversary patch attack. This is also these are some results that are published, and right off the box, it performs at 41%. But in comparison to ours, which the best one is performing at 89.1. Okay. Furthermore, we did, well, how does the volumization depth impact defense accessory? So we did 4x4 6x6, 8x8 patching, and increasing volume depth. I'll show you some of what I mean by this. And the larger the patch size or the smaller the volume depth is, the better the performance, the defense success rate is. Okay. Okay. So the smaller the patch sizes, i.e. the attack pixels will probably span multiple patches. In that case, we start to see performance that is low. And as you increase the patches, i.e. such that the attacks are contained within a single patch, and I believe the model is circumnavigating or producing better results by using the remaining patches in that volume. So we see better performance as you increase the patch size, decreasing the volume depth. Okay. Although I want to say the x-axis in this case can be misinterpreted. Well, how do we do if we want to calculate the generalization capability, if we were to deploy to real-time setting? You do want to care about the F1 scores, the accuracy, the AUC, the ROC, all of those metrics that capture real-time scenarios, class imbalance, and other things. Okay, and then in that case, we also notice that the defended model is a lot better, almost I would say, orders of magnitude better than the undefended models in both cases. I think the last piece is, or maybe is one more after this, is to see, well, which one of these key components is contributing to the defense of these models. So here I have mutual information defended model only with volumization, and then I have defended, MI curriculum learning trained model without the volumization. And then the MI is both of them combined, or the complete system. Okay. And you can see the curriculum learning doesn't really have significant impact on defense. Okay. This is, if I were to put it side by side with the undefended model, then this is probably on par with the undefended model under attack settings. Okay. But if we look at the volumization trained model, i.e. you turn off the curriculum learning, you lost, a little bit of accuracy, but performance is higher than the just curriculum learning only model. And then when you combine the two, you produce better models in generalization under attack conditions, and then also under for the clean data set. Okay. We have in the past, we've published a few papers showcasing the improvement results that you see by employing curriculum learning training. Okay, so I guess here the conclusion is the volumization, I believe, is what is contributing to defense as opposed to the curriculum learning components. Okay, as far as timing information, I guess to be fair, I have, one has to say, well, you have increased the number of parameters of the models. You're doing all of these pre-processing of images. Well, is that really something that we want to tolerate? Is that fair? As far as the timing and overhead, is that going to be a trade-off that we tolerate? And then I guess in that sense, at inference time, although some of these increases are significant, we do see an average increase in about 6 milliseconds on average across the different models. In some cases, it's almost double. So for instance, going from inception, going from a defended to defended model, you're almost doubling the inference time, partly because you have increased the number of parameters of the models. Okay. In training setting, this depends on the data set. but this can range from hours to days in terms of overhead. But I say you will be fine because you're guaranteed a defended and secure model, and you're able to tolerate these overheads, but also we can produce these syllabuses or these syllabi to be used without you having to, I guess, incorporate the curriculum learning into your training pipeline. But we can give you the syllabus of CIFAR-10, CIFAR-100, and then you can train your model using that syllabus without having to do the curriculum learning implementation in your deep learning pipeline. Okay. Do I have time to show a couple of images, qualitative results? Okay, I'll go ahead and show you some of the results that you would see. So here, for instance, you have a cat image. This is blown up, and that's why it's highly pixelated. But a cat image, when you attack it with 1 pixel, it is classified as a sheep. Can't remember which model this is. EfficientNet. It's classified as a sheep by EfficientNet. And then when you split it up into 4 patches, attack it with the same pixel, you get a prediction of 50, a cat with 50% accuracy. Okay, that's under when you have a depth of 4 in this case. Same goes with 2 pixels. And as you increase the attack magnitude, you're still sort of maintaining the accuracy of the model, although I'm showing the good results here. And then, similar results was with the APA, the patch attack. You have a ship here, and then you have a toaster patch that's being pasted on the image. Okay, the VGG would classify this as a deer with almost 100% accuracy. And then if you defend it with a 16 depth volumization algorithm, you will end up getting a correct prediction with about 87%. Okay, so this is what we want to achieve. A few other images I want to show. So if I gave you, if you gave me this image, which is the original sample, what the volumization algorithm does is it creates these different patches. It analyzes each patch and says, hey, this is how you want to produce images, the patches into the model. And what I want to highlight here is you can see that the high entropy samples, and I'm using entropy here, the high entropy samples have limited features of interest than the low entropy samples. And this is sort of the point of curriculum learning in general, is to create an input path by prioritizing important features or more complex features and deprioritizing less complex features. Okay. And I'm saying what I'm highlighting here is these sort of inherent characteristics as captured by entropy, mutual information, etc., they do seem to offer some insight as far as the sort of natural characteristics of the pixel distributions are concerned. Okay. This is the same, but I think this is depth 16. Okay, each image is 256 by 256, or each patches, and then the original image is 1028, blown up for quality reasons. Okay, I guess I'll stop here and see if you guys have any questions.